All right, welcome back to the Kitchen Group. Today I'm going to tell you about a new paper we have published recently on surface segregation studies in ternary noble metal alloys. And we use DFT and machine learning, and we compare with some experimental data. So in a nutshell, the challenges in alloy segregation is shown over here on the right in this little multicolored cube that looks like a ternary metal alloy. We have a bulk composition and a surface composition that are in equilibrium with each other, where the surface has a different composition than the bulk because it has a lower surface energy. For example, here it's depicted as gold. Gold has a lower surface energy than palladium or copper, and so gold would tend to segregate to the surface and have a different composition. The challenge in modeling this is you need a large unit cell like the one shown here. This is probably 1,500 atoms, and we can't calculate that with DFT because we need to calculate all the possible configurations to see which one has the lowest surface energy. And this problem gets exacerbated when you have a ternary alloy because that increases the configurational space. You get 3 to the n possible configurations that you want to be able to evaluate. And we have different surfaces, so there might be a 111 surface or a 100 surface or a 110 surface. So this is out of the question to do with DFT. And in the past, we've used machine learned potentials to study a binary alloy like gold palladium. But the challenge that we had in the past was really one of transferability. That 111 model that we had couldn't be applied to the 100 or 110. And so in this work, we've made a couple of advances in that. One is we use a much more flexible machine learned potential from the Open Catalyst project, and it is already pre-trained on a very large number of other systems, and then we can fine-tune it on a comparatively small number of 111, 100, 110 surfaces, and then we can use that machine learned potential inside of a Monte Carlo loop where we can sample that configurational space and eventually calculate segregation energies and then compare those to what we can find experimentally. So we do find qualitative agreement in the sense that we see gold segregate when gold is supposed to segregate, but quantitative agreement is limited by the DFT calculations. And so we overestimate how much gold should go to the surface and we underestimate some other properties. Okay, so let me tell you about the simulation tools. We use DFT, we use VASP. We tried 2 different functionals, PBE Sol with D3 van der Waals interactions and the regular PBE functional. I won't talk about it in this video, you can read the paper. We mostly were trying to make sure that there weren't any systematic issues with one functional or another. They both have limitations. We trained all these different sets of data points over here, the 35, less than 35 atom slabs, 60 atom slabs for validation. We have a whole bunch of these that go into a learning curve model. We figure out how to test for convergence and that we have a good MLP. And once we have an MLP, machine learned potential, that goes into the Monte Carlo model, and that's where we simulate the segregation. For Monte Carlo, we do 10 by 10 by 15 slab, so these are randomly initialized at the desired composition. Then we swap atoms and calculate the change in energy, and if the energy change is negative, it gets accepted, and if it's positive, it's accepted with a Boltzmann probability, and we do that until we reach a converged energy with no big changes. And so we did this for 3 alloy systems on 3 surfaces, and we did 200 Monte Carlo simulations per surface, and that allowed us to map out the entire composition space. All right, so a typical Monte Carlo result for one simulation might look like this. We have, let's see if I can turn on a laser pointer, and you can see it. We start out with a bulk composition here. And as we allow the swaps to occur, we see an evolution in the surface composition. So here is probably gold. It goes up and then it oscillates and fluctuates around some steady-ish value. and you see something like palladium going down to near 0. So the end result of this one is you start out with purple in the surface and you end with no purple in the surface. And you start out with a little bit of gold and a lot more comes to the surface. So this is what we did for all these 3 surfaces and all the 3 alloy systems, about 1,800 in total. And this is this trajectory step down here tells you why we can't use DFT. This would have been over 7,000 DFT calculations on a 1,500 atom unit cell just for this alone, and now multiply that by 1,800. That is an enormous amount of compute time that nobody is going to do. But with an MLP, it happens, and we were able to do this in a matter of weeks. There's a lot of results in the paper. It's open access. You can go see it. I'll highlight just this one estimation of the surface energies that we looked at. These figures take a while to study, and so we have here the gold, silver, copper sample. So if you look down on the left, this is a color-coded version of segregation energies across the different for the different pairs, so silver gold, copper silver, gold copper. And if you look from left to right here, I show the PBE Sol 110 surface. This is the one that appears most consistent with the experiments. I should note the experimental data is a thin polycrystalline film, and we don't know how much 111, 110, and 100 are present. So it's a little bit challenging to figure out exactly how to make these comparisons. But the 110 is consistently the most consistent with the experiments, and so we highlight that data here. And then on the right, we have a different system, copper, palladium, gold, and we have the experimental data here, and the PBE and PBE Sol are shown over here. You see some qualitative similarities and some quantitative differences, especially down here in this space. All right, so in summary, this paper is all about a computational alloy segregation study. I believe it's probably the most comprehensive that I know of to date. We looked at 3 different ternary alloys on 3 different surfaces across the complete composition space with the machine learned potential that practically has DFT level accuracy. We could update it with new DFT functionals that come up down the road. But then we just need the data and to retrain it. The Monte Carlo allowed us to do surface segregation at different temperatures, and then we could take those compositions that we modeled out of the Monte Carlo and perform like an equilibrium analysis to figure out what the segregation energies are. The results are qualitatively consistent with experimental results. But our paper shows the accuracy is probably limited by DFT and in particular the strength of the metal-metal bonds and errors that happen at the surface because of the functionals. There is also some experimental uncertainty in the surface distribution, but that experimental data set is also the most comprehensive experimental data set available today. There's just nothing else available for calibrating these methods. So the paper's open access. You can find the link in the video description. Check it out, and I hope you enjoy it. Thanks for listening.